Good morning, everybody. It's Tuesday. Happy Tuesday. Hopefully everyone had a great long weekend, 4 days. That's terrific. If you could begin with some green check marks, I would like that. As well, if you had any questions from the beginning stuff that we covered last day on radicals. I shouldn't say that. We didn't get quite into radicals. We talked about the real number system. So the first, I think, 3 pages of the learning guide dealt with the real number system. If you ran into any problems there, you can just throw the page number, question number into chat, and I will do my best to answer any questions you might have had. And we're going to take about an hour today. We do have I don't know what we'll call it. We'll call it a spotlight, I guess, this afternoon, not this afternoon, a little bit later this morning in kind of where you'd normally have your second block. So we're going to sign out a bit early so we can set up for that. And I'll explain that a little bit later at the end of class. So hopefully everyone had a great long weekend. Ate some food and did long weekend things. I don't see anybody throwing any questions into chat. I do see Jonah typing. Give him a second. I'll just maybe talk a little bit about what we covered last day. All right, Jonah, is it like a formatting thing? Was it putting numbers and symbols and getting them all mixed up? Because that's pretty common with these learning guides. I don't know if it's the version that Word, the version of Word that it was created in, or what the deal is, but it happens. So what I can do is, if you guys continue to run into problems with all the formatting and stuff, just let me know, and I can just download it. I think it is a PDF already. Yeah, your symbols, Eric too, hey? There should be a way that I can go in and, yeah. I'll put another copy of it up this afternoon for you guys. So if you did run into problems with formatting, it looks like Eric and Jonah both did. So I'll do my best to get another copy up that shouldn't have the same problem. So if you do run into that, just let me know and we can make it work. If it ever does happen, it's not really the end of the world if you can kind of try to figure things out. Later on in the course, when we start doing exponents and things like that, it'll get a little bit worse possibly, so I'll have to remind myself to try to get you guys a version that'll work for everyone. But if you're running into problems, just a suggestion to maybe a first place to look would be to update your Adobe, because I think all those learning guides come out as PDFs, which is an Adobe product. So if you go into your start menu on your computer, if you're a Windows user, and you go find Adobe and just open it up, and then in the top corner there should be like a help button or something, and then you can just say update. Usually that's in the help or in the help menu, and that would be good. Or you can just go to Adobe's site and then download the latest version of Adobe. So I will do 2 things for you guys. I will upload a version that should work for everyone without any formatting issues, and I'll put a link to Adobe's updating page in the course, maybe up at the top somewhere, and that will kind of hopefully alleviate some of these problems. So if you ran into issues, it'll be okay. Yeah, I don't see a ton of people writing questions, but last class we did 2 things. We finished off talking about the real number system. So we drew this diagram right here. In the middle we have natural numbers, so 1, 2, 3, 4, 5. Then the next circle is whole numbers, and then we had integers, rational numbers, and then irrational numbers. And remember, we always have the most inclusive in the middle, and then as you go out, like the number 1, it goes into it's everything in terms of these circles. So 1 is rational, 1 is an integer, 1 is a whole number, and 1 is a natural number. But if you have something like the example we included up here, this -7, well, because it's negative, it's just an integer. That's the sort of the biggest circle it'll fit into. So we talked a little bit about that. The learning guide had some questions on it. And then we jumped into lesson 2, but we didn't get very far. So let's just finish off lesson 2. And then we'll move on to lesson 3. I might not get through all of lesson 3, but I want to get the majority of it done. And that way you guys will be about halfway done unit 1. It's a really short unit. Unit 1, I think there's only 4 lessons. So we only have this one class this week. Next week we'll finish off unit 1, and then we'll go kind of jump back into unit 3 because we've done 2 already. So this chart we had at the top of the page with all of your perfect squares, perfect cubes, and perfect fourth powers. And this is a good reference for you guys to use if you haven't sort of memorized them. When you start getting into these questions, you'll see that numbers like 16, 64, 81, all of these perfect squares and perfect cubes, they come up again and again and again. So it's important that you know these, but they'll start to come a little bit more naturally as you go. And you just encounter them again and again. So it makes life a little bit easier, but the more you know, the better you'll do. So the square root part of the chart leads. This like second or third row here is what you're talking about, leads, I assume? Square root. I guess we're taking the square root of the previous one. So the square root of 4 is 2, the square root of 9 is 3, square root of 16. That, I guess, is confusing. The important thing is that you know the squareds column and the cubes column. And those are kind of the important numbers. If you just kind of ignore this and ignore this, you'll be okay. So you just need to know your perfect squares and your perfect cubes. I guess it was just a way of showing them that I didn't execute very well. So let's look at a few of these to just get warmed up. Are these equivalent? So when we are dealing with radicals, it's important to treat them kind of like brackets. And we'll learn later, I forget what unit, I think it's unit 4, that when we have something like this right here, you can write this exactly the same as it is, 81 plus 16. And without going into too much detail, you'll just have to believe me for now, you can write this to the power of 1/2, and it's in brackets. So if we're dealing with these radicals, we want to deal with them in terms of bed mass, brackets, exponents, division, multiplication, addition, subtraction. Radicals will always fall into the brackets category. So it's the first thing you have to do. Anything under a radical sign is the first thing. It's the B, it's the bed mass, brackets. Because we can write radicals like this, the square root of 81 is 81 to the power of 1/2. That's just the same way of writing something. They're equivalent. So that's kind of why they're brackets. You'll have to trust me for now, and we'll explain a little bit further down the road. But there you go. So if I deal with anything under the radical sign as if it were in a bracket, I would have to do 81 plus 16 first, because anything inside the brackets I'd have to do first. So I'm going to rewrite this. I'm going to write, instead of 81 plus 16, I'm just going to add them together. So it gives me 97. The square root of 97, I don't know what that is, but my calculator does. Square root 97, it gives me 9.85, we'll call it. All right, so the square root of 81 plus 16 is 9.85. Now let's do them separately. So the square root of 81, we know what that is, it's 9. And the square root of 16 is 4. Those are two perfect squares. 9 and 4 added together gives me 13. So these things are not equal. So that means whatever we started with is not equal. So if I'm adding something under a radical sign, it's not equivalent to adding the two things that are individual. Now, you're probably thinking, Mr. Borden, why does it even matter? What do I care? Well, let's look at B and then we'll see why it matters. All right, so again, we have something under a radical, so we're going to treat it like it's in the brackets. So we're going to do the multiplication first, and then we'll do the radical second. So the multiplication here is 81 times 16, and I don't know what that is, but I'll do it on my calculator. 1,296. So we have the square root of 1,296. That's a big one, so I'm going to take the square root of 1296, and that's 36. That's good. All right. Let's do the next ones. So the square root of 81, we'll deal with that first, is 9. And then we have times 4. Again, perfect squares, 9 and 4, 81 and 16. 9 times 4 is 36. These things are equivalent. All right. Was it just by chance that that one worked out really well, or is there some sort of mathematical property we can kind of generalize to here? That's where we're going to. Let's look at 2 more examples to try to make sure we, if we can figure out sort of there's a pattern happening here, then we can just generalize it to all multiplication or subtraction. So we looked at some addition. Let's look at some subtraction. 100 minus 4. It's going to give us the square root of 96. I don't know what that is. Uh, 9.79, we'll just call it 9.8. All right. And then if we do them separately, the square root of 100 is 10. Then I'm going to subtract 2, which gives me 8. So these things, again, are not equal. Nowhere along the way are these things equivalent. Let's do this last one and see if we can kind of generalize it a little bit further. 100 times 4, so if I deal with the bracket first, I'm going to get the square root of 400. And the square root of 400 is going to be 20, because 20 times 20 is 400. Here I have the square root of 100 is 10. The square root of 4 is 2. All right, so these things are equivalent. So if we were to, we could test out a bunch more examples, we could try to prove it, or you could just trust me, we've looked at 2 examples. If we have something under a radical sign and it is multiplication, we can generalize it and we can break it into 2 things if we want, or we can leave it together. It's the same. If we have addition or subtraction under a radical sign, we cannot break it into 2 parts. That's kind of what I was trying to get at here. So we're going to use this very important property of radicals over here. We're going to use that in the next lesson. All right. Evaluate the following to the nearest hundredth if necessary. All we need to do here is just test your calculator skills. So there's nothing here that really is meant to be really difficult. You'll find questions like these on tests. They just want to know if you can kind of just estimate what these equal, or evaluate, I should say. So it's just a matter of using your calculator. Now, everybody's calculators are going to be a little bit different. For some of you, you'll have to put in, if we look at this first one here, you'll have to put in 34, and then you'll have to hit the square root sign, and then you have to multiply that by -2, and then get your answer, kind of working backwards. For some of us, we could just write it in our calculators as -2 root 34 and hit enter and see what we get. It just depends on how your calculator works, and that's literally half the battle here. So with the calculator I've downloaded here, I should probably put the link to this thing in there too, so you guys can download this calculator if you want to use it. All these good ideas just coming to me. Must have been all the turkey I ate this weekend. It's got my brain working. Everything's good. All right, so what I'm going to do is I'm going to go -2, and then I'm going to put in the square root of 34. Because I know this calculator can just, I can just write it in as I see it, and it should give me the answer for something kind of simple like a. So let's see what that equals. -11.66 to the hundredths place. It's really, really important that you actually try this on your calculator. Don't just take my word for it. You need to make sure you know how to use your calculator. If it's not coming out as -11.66, then ask and we can figure it out together. But it's super important that that works out to be the same thing. All right, letter B. I could probably plug this all into my calculator in one big step. In fact, I know I could. But I kind of like to do it maybe in 2 steps just to kind of minimize mistakes. So let's do this. Now I've done it. All right, I'm going to do it in 2. So I'm going to go on the top. I'm going to do the top first. So I'm going to go 10 times the square root of 12. I can hit enter. That gives me 34.64. And I'm going to divide that by 5 times the square root of 18. So 5 shift square root 18 equals 21.21. And then I'm going to divide those. So 34.64 divided by 21.21. That gives me 1.63. All right, so there's to the hundredths place. Just for fun, I'm going to see if I can put this all into my calculator in one step. And I'll do my best to kind of explain it as I go, but calculators are really smart, but they're really dumb at the same time. They're not good at order of operations. So if I put things into my calculator, sometimes my calculator takes them quite literally, and I need to start including brackets. So what I'm going to do is I'm going to just do the top like I normally would. So I can just go clear. I'm going to go 10 times the square root of 12, and then I go divided by, and then I'm going to put everything on the bottom in brackets. Now the reason I'm going to do that is because if I put divided by now and then put 5, what's going to do is my calculator is probably going to go 10 times the square root of 12, and then it's going to divide it by 5, and then multiply everything by the root of 18. It doesn't know that that root 18 is also on the bottom, so that's why the brackets are important. So I'm going to go bracket 5 root 18, and then I'm going to close the bracket, and then I'll hit enter and see what I end up with. It just turns out to be the same thing, which is a good thing. So if you have a calculator kind of like the one I'm using here, then you can just put it all in, assuming you know where to put brackets and things like that. So let's look at the last 2 here, and then we'll move on. All right, so letter C, square root of 21 through root 7 minus root 8. You can put it in one step if you want. You can do it in 2. I'm going to do it in 2. So I'm going to go square root of 21. On the top I get 4.58. And then I'm going to have uh, 3 times square root of 7 minus square root of 8. I get 5.1088. So we'll go 5.11, just to round. And end up with 0.896. We'll call it 90 once we've rounded it. Let's try to maybe do that all in one step, see how that goes. I'm going to go square root of 21 divided by bracket 3 root 7 minus root 8. Close my bracket. And 0.896, get the exact same thing, around to the hundredths place, and I get 0.90. There we go. This last one's the exact same thing, except you have cube roots. I'm just going to plug it in. I'm going to go, I have a cube root button on my calculator, but if you don't, you're going to have to go 3 root with a little x in front of it, 72 minus, I'm going to put everything in brackets here, 2 I don't know if my calculator is going to be smart enough to figure this out. I might do it separately. All right, I'm going to take a step backwards here. Let's take the cube root of 72 first. So I'm going to go 3 with my root, 72, and that equals 4.16. Then I go minus 2 times the cube root of 51. So I'm going to go 3 again, my root, 51, that's 3.70. There we go. So you can do it in 2 steps, and then I'll check and see if my calculator knows what it's doing. So I'm going to go 4.16 minus, and then I go bracket, 2 times 3.70. Putting things in brackets in your calculator is really helpful for order of operations. Make sure everything works. Negative 3.24. Now let's pretend that I want to do it all in one step. Let's see if I can do it. So I'm going to go 3, because I want to take the cube root of 72. I'm going to subtract. This is where I think it's going to get confused, because I'm going to go 2, then I'm going to go 3, and then I'm going to go like that. And if I do it this way, it's going to take the 23rd root of 51, which isn't what I want, but that's what it's in as. So I wonder if I backed up a little bit. I wonder if I went 2 times, and then I did the 3 root 51. Yeah, that works to be the same. So you just got to watch how you're entering these things in your calculator. How do we all feel about question number 3 there? Are we good? Are we ready to move on, or did anybody have any questions about how that's getting entered, brackets, order of operations, anything? Got about 30 minutes left. I want to get into the next lesson. We're good? Thumbs up, thumbs down, smiley face, frowny face, confused-y face. Yeah, last one for sure. Anybody else So what I wanted to do was, I wanted to just make sure I did everything right. So I kind of broke it down into two steps. My first step, and then I actually did the calculation. I could do it into 3 steps if I really wanted. Let's start with the cube root of 72. That is 4.16. So I'm going to just use the cube root button. 72, that's 4.16. All right, so 4.16 for the first half. And then I'm going to subtract 2, and instead of writing the cube root of 51, I'm going to calculate the cube root of 51. Which is 3.70. So now I have 4.16, which was the cube root of 72. I'm just kind of carrying that down. And then minus 2 times the cube root of 51. So I'm just kind of focusing on the second part right now. 2 times the cube root of 51 is 2 times 3.70, which is going to be 2 times 3.7 is going to be 7.4. And then I do the subtraction, 4.16 minus 7.4. Negative 3.24. So we can do this all in 1 step. We can do it in 3 steps. Doesn't matter, whatever you're comfortable with. What I find, generally speaking, is the fewer steps you try to do it in, the more likely you're going to make a mistake, which seems kind of counterintuitive because you'd think, oh, you've taken all these extra steps. But those extra steps are there to make sure you are doing everything properly. So taking each sort of mathematical operation and doing it by itself, and then kind of following through with BEDMAS, essentially. You're welcome, Leeds. There is the end of lesson 2. This next lesson is kind of the meat and potatoes of this, this unit. So kind of a weird concept. I shouldn't say it's weird, but it's kind of, we'll call it like a light bulb concept. As soon as you get it, you're like, this is so easy. But until you kind of get there, sometimes you get kind of confused along the way. It's not difficult. The math is, stuff you've been doing for a long time, but we're just taking a couple concepts that you've seen before and just putting them together. Fractions can be written in many different ways. So 4 over 16. Can anyone think of a few ways of writing that? You just throw it into chat if you want. What's another way of writing 4 over 16? So essentially, these things are all equivalent. 4 over 16 is the same as or equal to. Anybody think of another way to write 4 over 16? 1 over 4. Perfect. What you've done there is you've simplified. You said 4 goes into 4 once, 4 goes into 16 4 times. Jonah, 2 over 8. I love it. That's equivalent to 2 over 8. Again, Jonah, you've pulled out 2's from the top and bottom. So 4 divided by 2 is 2. 16 divided by 2 is 8. I don't have to necessarily go smaller. I can, make this thing bigger. So I can multiply everything by 2. I can go 8 over 32 if I wanted. There's nothing wrong with that. And every time I do this, if I go 4 divided by 16, I get 0.25. I go 2 divided by 8, I get 0.25. I go 8 divided by 32 on my calculator, I get 0.25. They're all completely equivalent. So I can write these things different ways. It doesn't change the actual value. In some instances, things are just going to work out a little bit better than others. 400 over 1600. For sure. Same thing. And again, 400 divided by 1600. Big numbers, big scary numbers. Plug them into my calculator, I get 0.25. I go 1 divided by 4, I get 0.25. I go 4 divided by 16, I get 0.25. These are all equivalent things. I could write 400 over 1600 if I want. I could write 1 over 4 if I want. they're all the same. I like 1 over 4. We usually simplify fractions because as numbers get up to like 400 over 1600, they get a little bit difficult to multiply by 7 and things like that. But if I'm multiplying 1 over 4 by 7, well, that's just easy. It's just multiplied by 7. So we can, using the same sort of thing in what we just looked at in the last lesson, we can actually use a property that we looked at to kind of write radicals in different ways. So we discovered that if we take the square root of 9 times 25, both under the radical sign, that's going to be exactly the same as the square root of 9 multiplied by the square root of 25. It doesn't matter if I write them like this or if I write them like this. I get the same thing. That is not true of addition and subtraction under a radical sign, which is extremely important. But as long as I have multiplication or technically division, well, let's just stick with multiplication for now. As long as I have multiplication under a radical sign, they can be all under one radical, or we can split them up, and I'm going to get the same thing. So let's just look at this. I don't know what 9 times 25 is. Actually, I do, but let's just plug it in anyways. 225. And then the square root of 225 is 15. That's perfect square. 15 times 15 gives us 225. Or I can go square root of 9 is 3 times square root of 25 is 5, which gives me 15. These things are equivalent. We're going to use that property for the rest of this unit now. So just as it is with the square root, the same property is true for cube roots. So it doesn't matter what the root is, we can split it up as long as it's multiplication. So 8 times 27, I don't know what that is, 216. The cube root of 216, that didn't work out, 216. That's 6. So 6 times 6 times 6 gives us 216. Or the cube root of 8. Cube root of 8 is 2, because 2 times 2 times 2 is 8, or 2 times 2 is 4 times 2 is 8. And the cube root of 27 is 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So 2 times 3 gives me 6. So it's true of cube roots and square roots, and it doesn't matter what root I am taking, the property remains true. So we can generalize this, and that's what this little orange-ish box is saying. Now, I find sometimes that the way that we write these laws in mathematics, they look really, really confusing. It's a really simple idea. We can take the multiply both things under the radical sign, or we can split them up, but as long as it's multiplication, they're equal. This kind of is telling us that for all numbers. So let's try to read through it and see what it means. This says the nth root of a times b is equal to the nth root of a times the nth root of b, where a and b are real numbers. So a and b can be anything. If you think about the real number system, real numbers could be negative 7.15, 17, it doesn't matter. But n has to be a natural number. So this is where the definitions of these words start to become a little bit important. Natural numbers are the counting numbers. So 1, 2, 3. We don't include 0, and we don't include negative numbers. So this is anything from 1 to infinity. We don't take the square root or the negative root of numbers yet. We will, but not yet. So we can use this property to simplify square roots and cube roots that are not perfect squares or perfect cubes, but have factors that are perfect squares and perfect cubes. So what we're saying here is if we end up with a radical sign that doesn't have a perfect square under it, we can make it a little bit simpler, a little bit easier to deal with. Just like when Jonah said at the top of the page, 400 over 1600, well, I'm going to guess that very few of us would probably want to deal with that in sort of a mathematical way, in an equation. That's really big numbers, 400, 1600. I don't know my 400 times tables very well, or my 1600 times tables. But if I were to write this as 1 over 4, that makes it a lot easier. I know 1 times just about anything, well, everything, and my 4 times tables are pretty good as well. So it just makes it easier to deal with. And that's what we're going to do with radicals now. Instead of dealing with something like, I can't even think of something off the top of my head, but we'll look at some examples. We're going to be able to start to simplify radicals that don't have perfect squares under them. So if I end up with a square root of 25, awesome. Perfect square, 5 times 5 is 25, done. But if I end up with something else like the square root of 75, well, that's not a perfect square, but I can simplify it because it does have a perfect square that's a factor of it. So this is why we kind of talked about this little chart here at the top of lesson 2. All these perfect squares and perfect cubes are going to become very important now. So if you even want to have this chart out while you're doing the rest of today's lesson, I would strongly recommend it. It'll make your life a lot easier until you get a good grasp of the perfect squares and perfect cubes. So a mixed radical and an entire radical, these are kind of definitions we need to go with. So a mixed radical is a product I shouldn't say a product. I'm going to go with a number. Sorry about that. A number written as a product of a number and a radical. So we'll talk about mixed radicals, kind of like mixed fractions. You guys have dealt with those before. And entire fractions, exact same concept, mixed fractions, entire fractions. Now we're just extending it to radicals. So we have mixed radicals and entire radicals. An entire radical is a radical with a number under it. That's not like a math definition. That's just a Mr. Borden, keep it simple type definition. So maybe let's look at a couple examples of these before we move on. A mixed radical is a number written as a product of a number and a radical. So we could write something like 2 times the square root of 7. That would be a mixed radical. An entire radical would be like the square root of 12. If we put a number in front of it, mixed radical, no number in front of it, it's an entire radical. All right, I think we're doing good with time here. We'll power through these 4 examples, and I think we'll probably end there. All right, the square root of 63. Now, notice that this question doesn't say evaluate, it says simplify. And that becomes important. If it said evaluate, I would plug it into my calculator. The square root of 63, what does that equal? Whatever it is. I don't know what that is. Square root of 63. It's going to be between like, I don't know, 7, 7's 49, 8 and 8 is 64. It's just smaller than 8. But I don't want to deal with 63 because 63 is a big number and I don't like big numbers. So I want to simplify it. What I need to do is this. Now, at first this is going to seem a little bit strange, but you just got to get used to kind of the process and you'll be fine. I need to think, is there anything I can break down 63 into? So I'm going to kind of factor 63. 63 is just two numbers multiplied by each other. But what I want to do is pick perfect squares. So are there any perfect squares that go into 63 an integer amount of times? So can I multiply any perfect squares by another number to get 63? Now I can. I'll do the first one and then I'll give you guys a look at the next few to see if you kind of get what I'm getting at. So instead of writing this as 63, what I'm going to do is I'm going to make a big radical and I'm going to think, what are the perfect squares that go into 63? I know that 9 is a perfect square, and 9 times 7 gives me 63. So what I've done is I've said, okay, 63 is not a perfect square, but there is a perfect square that will actually divide into 63 a whole number of times. Now, using the property that we looked at above in that little orange box, what I can do is instead of writing this as one big radical, if I'm multiplying under a radical sign, I can split it into two radicals. So I'm going to go like this. I'm going to go the square root of 9, and then I'm going to multiply it by the square root of 7. Now, the square root of 7, I won't be able to simplify, but the square root of 9 I can. I know that the square root of 9 is 3, and I have this root 7. Holy cow, Mr. Borden, why would you even bother doing that? Well, it's just to simplify it. I don't know my 63 times tables, but I do know my 7s. So it made everything just a little bit easier by pulling out a perfect square. Now, is the square root of 63 equivalent to 3 times the square root of 7? We should probably check that to make sure that we just didn't make up a bunch of smoke and mirrors and hope that it all worked out in the end. So let's take the square root of 63. That gives us 7.9. And then if I take 3 times the square root of 7, I get the exact same thing. So those are equivalent. Just like I'd had at the very beginning, 400 over 1600 was equivalent to 1 over 4. It doesn't matter how I write them. They're equivalent. One's just simpler than the other. So these two things are the same. There you go. Just made it a little simpler. All right, square root of 200. 200, not a perfect square. I can go square root of 200 in my calculator if I want. But it's not just a nice integer number. It's 14.14213562. That doesn't help me at all. Can anyone think of a perfect square that goes into 200? What is the biggest perfect square that goes into 200? Are there any perfect squares that goes into 200? There's a couple different ways to do this. Things get a little bit tricky when we look at this one. If I think really, really hard and think, okay, 200 perfect squares, I've got 4, 16, 25, 36, 49, 64, 81, 100. 100 goes into 200. So instead of writing this as the square root of 200, I'm going to write it as the square root of 100 times 2. Because I can take the square root of 100, but I can't take the square root of 2 because it's not a perfect square. So instead of writing it as one big radical, I'm going to split it up into two smaller radicals. Square root of 100 times the square root of 2. And the square root of 100 is 10. I don't know what the square root of 2 is, so I'll just write it as 10 times the square root of 2. Again, we can check it in our calculator. If I go 10 times the square root of 2, I get 14.14213562. It's the same thing. I've just written it in a different way. Now, we do run into one problem with questions like this one, and you'll hear me say it again and again. I'll say, what is the largest perfect square that goes in? Because if we just look for perfect squares in general, I could have broken 200 into, what's another perfect square that goes into 200? I think 25 goes in there. And it goes in there 8 times. All right, I can break this up. 25 and 8, and then square root of 25 is 5. So why did I get something different here? I mean, mathematically, these are equivalent. If I write 5 root 8 into my calculator, oh, I missed the 5. 5 root 8, I get that say 14.14. Why don't these look the same? How can I get 2 different answers for the same question? Well, I ran into a little bit of a problem here. Square root of 8 has a perfect square that goes into it. 4 goes in there. So when I get here, I'm not quite done. I can break 8 into 4 times 2. So I'm going to have 5 times square root of 4, which is 2, times square root of 2. 5 times 2 is 10, root 2. Now, instead of finishing here, now I've ended up with the same thing as I had there. So if you don't find the largest perfect square on your first try, make sure when you get to your answer, you say, are there any perfect squares that go into root 2? Or is that as simple as it gets? So we discussed that this rule, where we can break up a radical into 2 pieces, it's going to hold true for both square roots, cube roots, fourth roots. It doesn't really matter what root you're dealing with. It's going to be true. So this is why it gets a little bit important for you guys to know your perfect cubes. What is the largest perfect cube that goes into 108? I don't know. So just off the top of my head, 108, not ringing any bells. What are my perfect cubes? Well, I have 2 times 2 times 2 is 8. So I'm going to go 108 divided by 8. Do I get anything? 13.5. So it's not an integer. All right, 3 times 3 times 3 is 27. That's my next perfect cube. 108 divided by 27. Does that work out to be a whole number? It does. 27 and 4. Okay, so I'm going to take this 108. I'm going to rewrite it as the cube root of 27 times 4. I'm going to split this up into 2 radicals now. I got the cube root of 27 and the cube root of 4. The cube root of 27 is 3. And the cube root of 4, I can't calculate. It's going to be a decimal. The cube root of 4 isn't the same thing as the square root of 4. So make sure when you are going quickly through these questions, you don't just think, oh, cube root of 4, that's 2, and move on. No. The cube root is a number multiplied by itself 3 times. So 2 times 2 times 2 is 8, not 4. Let's look at the next one. 128. Again, I don't remember the largest perfect cube that goes into 128. So let's just check a few. 128 divided by 8 is 16. Maybe I'm going to go with 8. Let's see if there's any bigger ones. 128 divided by 27. Nope, that doesn't work. 128 divided by 4 times 4 is 16 times 4 is 64. So does 64 go in there? Yes, it does. So notice how there were 2 perfect cubes that went in there. It turns out that 64 is the biggest perfect cube that goes in, but 8 also worked out. And the problem I run into there is that I'd have to do another step. So I always want to find the largest perfect cube. So 128 breaks down into 64 and 2. So I have the cube root 64 times 2. I write it as 2 cubes. 64, 2. Cube root of 64 is 4. And cube root of 2, I don't know what that is, but that's the answer. So to make this process easier and reduce the number of steps, look for the largest. I wrote it in large letters so you wouldn't forget. I'm going to put 2 stars next to it. Largest. Super important idea. You can do these questions and you can get them all wrong even though you've done everything right if you don't pull out the largest perfect square, largest perfect cube right from the beginning. There's no shame in doing it in 2 steps, but it's really important that when you get to your answer, you gotta say to yourself, is there any perfect squares that goes into my answer? Is there another step? Can I continue this a little bit further? So what I'm gonna do is, it's almost 10. This last part here, I kind of hate that I'm ending at the middle of lessons, but that's just the way it is. This is kind of working backwards, so we'll get to this next day. What I'm gonna do is just check the learning guide and kind of see where we're at. So we talked about the real number system a little bit last class. We talked about number lines. We talked about estimating radicals, and I said finish up to the bottom of page 3 with the exception of this. So now we're looking, today is October 11th? Is that right? Yes, 10th month, sorry. Perfect. So today is October 11th, and this is what we're going to do. I'm giving away all these answers. So you should be able to do all of this stuff now. If you do run into problems, just ask next day. Should be good with that. Should be good with all of this. Just putting stuff on a number line. Decimal approximations. Evaluate each of the following to nearest hundredth. We did that in class today. Evaluate each of the hundredth. Yes. And you should be good up to there. Simplifying radicals. So this is what I want to look at today. So you get up to question 5 on page 6. So essentially kind of another 3 pages of questions for you to go through for next day. Get rid of all this stuff. So the bottom of page 5 and the beginning of page 6 is kind of what we were just doing. So write out the radical as the product of 2 radicals. So 18. Perfect squares that go into 18. I have the square root of 9 and the square root of 2. Is there anything else? I could go square root of 6 and square root of 3, but that doesn't have a perfect square. So this question asked me to circle the perfect square. So that's what that question is going to look like. Number 4 here, it just wants you to break these down. So 8 is 4 times 2, and square root of 4 times the square root of 2 is going to be 2 times root 2. So the square root of 8 is the same thing as 2 root 2. These do take practice. They do take time. And you guys will be really good at them by the end of all of that work. So essentially you're up to everything except number 5 on page 6. Should be done for next day. Hopefully that's clear. What I will leave you with is this. At 10:50, I don't know what Mrs. Wood said this morning, but at 10:50, maybe about 10:45, so you have 45 minutes to work on math or whatever. 10:45, you're going to sign back into the live feed, and we'll have a graphic up. And at 10:50, Mrs. Wilcox and Mrs. Ward will be in the studio here. And Mrs. Wilcox is an RCMP liaison for a school district, so that means she works for the RCMP, but she works in the schools as well. So she deals with students and things like that and youth. And she's going to talk a little bit about how she got into what she is, what it's like to be an RCMP officer, training and things like that. And I'm not entirely sure, but did Mrs. Wood say she'd be in Blackboard to answer questions or like pass your questions along, anything like that? I'm not sure if she mentioned anything. So if she did, then good. If she didn't, then just kind of sign in and see what it's like to be an RCMP officer. And if you do run into any questions, that we can send them along to Miss Wilcox after, our Constable Wilcox, and she'll get back to you guys. So I'm going to leave you there. Does anybody have any questions before we go? Yeah, this is our only class for this week. Yeah, you just log into the live feed. So you'll have to close this one, come back in about 45 minutes and log into the live feed again. And it won't say Math 10 anymore. It'll say something like Career Spotlight RCMP, or I don't know, whatever Mr. Ross comes up with that's witty and creative will be there instead of Math 10. So you just click back on the live feed. There'll be no chat. If Mrs. Wood didn't say there'd be chat, then there'll be no chat. So you just sign in and you see what Constable Wilcox has to say. Maybe you'll learn something, or maybe you might be considering RCMP as a career option. That'll give you some insight into what it's like. So I'll leave you guys there. What are we doing? Friday is McMillan Farm, which is awesome. I go with my family every year. So hopefully, if I don't see you again in math, we'll see you at McMillan Farm. But it's really important that you get caught up in math up to where we are in the learning guide. There's a quiz in the course you can try, and a little game with radicals you can play if you want. But that's it. So I will see you guys maybe Friday, maybe next week. Make sure you're going through this stuff, and we'll see you then. Thanks.